Hi everyone, thank you very much for tuning to this video. And since you're watching this video, I assume you work with images or you're interested in images and especially scientific images. And maybe you are curious about metadata and hoping to learn a bit more about metadata, which is exactly what this video is about. And in general, on my channel, I talk about using Python to tease information out of your images. And if that is something that you are interested in, and if you haven't already subscribed to this channel, this would be a great time to pause this video, hit the subscribe button, and while you're there, try to find the thanks button if you're feeling extra generous. Okay, so as the title suggests, we are going to talk about metadata, which is very important to understand for various reasons, and I'll talk about that as we get into our Python code. And in fact, I added a whole bunch of information, a whole bunch of notes, I should say, into this Python file that I'm going to share with you. Look for the link down below under the description, and that can serve as your additional notes in case you need to refer to it in future. Okay, so with that information, let's just jump into our Python IDE and just go through it. And don't worry, even if you are not a coder, you don't want to do anything with coding, you will find this video to be very useful, and code will happen occasionally in the middle, but we are going to focus on understanding metadata, and primarily from various image formats. The common ones: JPEG, TIFF, GeoTIFF, and OME TIFF, and a proprietary format from a microscope company. So if this is, again, you're still here, so I hope you're interested in this content. So let's jump in. And as you can see here, I added a whole bunch of notes, and the goal for this video is not to go through the entire text and bore you, but at the same time, just look at a few highlights here. For example, what is metadata? In case you don't know, metadata basically literally means data that describes data. In our case, the data is images, so metadata, when we refer to metadata in this tutorial, we are referring to the data that describes the images. And how do you store this data? Because one thing you can do is have an image and a text file or something else associated with this image and take notes in that text file. But images travel. I mean, this image will go, you share it with someone, but it's very challenging to always associate this additional file with your original image. This is why it's customary to embed all the metadata into your images, which may make your image bulky depending on how much metadata you are after. But in general, that makes it a lot easier for these images to be in a single file. And also, while you update this metadata, if it's written to the same file, you can actually trace how the images have been actually modified. So a metadata is, again, this additional information. And what additional information can it be? It can be pixel size, it can be the location, it can be if it's from some sort of an experiment, like experimental setting, if you have a physician's name, if this is a DICOM image, that is part of your metadata. Now, why is it important? We already talked about it. Basically, if you're just looking at your fun images that you take on your phone, obviously on your phone nowadays, you can actually see where the location is. It tells you, hey, this one's taken in San Francisco, right? Or it has this geolocation tagged. And again, how is it tagged? We'll talk about that for JPEG images, but for travel images, it's important so you know when and where the image was taken. I mean, if you're just sharing it on Instagram, you're like, hey, here is me having dinner at blah, whatever that place is. But what happens if you just open an image like, I don't know, 20 years from now? What happens if your grandkids want to take a picture in future, maybe on your 100th birthday at the same location? Having the geolocation, having that metadata is very important for someone else to reproduce what you have actually done, which is the key for scientific image analysis anyway. And for scientific image analysis, in addition to having this reproducibility, of course, which is important, you need traceability and interoperability, right? I mean, your images, if someone needs to open them, having this metadata information can really help. And of course, we already talked about reproducibility. And metadata provides a detailed history of the image if it's written correctly, including what parameters were used for acquisition and what equipment was used and every other detail. You can practically write anything to your file, but what is worth keeping track of, like what's worth of What does it mean? I mean, who defines these standards? Like, for example, for a microscope, you can write so much information to your file, but is that really important? Do you need all that metadata information? So there are certain organizations or groups that actually define what metadata is essential. And again, I'll briefly talk about it as we go along. And which is what I'm talking about, standardized, right? So what we're talking about is standardized metadata, because anyone can write anything. But do we care about what someone else has written? Or what if the metadata is incomplete, because you cannot complete your experiment if you don't know certain parameters? Someone needs to standardize this metadata, and they allow for different software and systems to understand and interpret this information consistently if you have that standardized metadata. And metadata contains essential information. Again, we already talked about it when it comes to scientific images, about the setup, about the conditions. So reproducing makes it a bit easy. So in this tutorial, I'm going to actually go through a few images. We'll open those images, and they include JPEG images. They include DICOM, TIFF, GeoTIFF, OMITIFF, and CZI. I think this covers a broad range of image formats and any other proprietary formats. Think of it very similar to .czi file. Okay. Again, we'll go through this. I hope this is not going to be a very long video, but this gives you a quick idea of what we plan on covering here. Okay, moving forward, JPEG images. Okay, so where do you get? I mean, practically it's everywhere, right? You take a photo on your phone, or you download something from internet. Chances are they're either JPEG, GIF, or PNG. So JPEG images, the metadata is standardized, and the standard used is called EXIF, right? I mean, if you are processing raw images from your digital camera, it's got this EXIF information. What does it stand for? Exchangeable Image File Format. And JPEG stores basic metadata like date and camera settings and location and the EXIF header and all that stuff. Now, who defines like what to store? Again, for JPEG, it is Japan Electronics and Information Technology Industries Association, JEITA. They produced the initial definition of this EXIF standard, and now today, these guys, along with another organization, CIPA, which I also believe that's based on out of Japan, they both define and maintain the EXIF standard to ensure the compatibility and, of course, uniformity in your metadata across all various devices. So any JPEG image, actually, let's do one thing. I have a couple of images. Let's just look at the image, and let's drag the image into a notepad to see if we can see anything readable. Okay. Okay, so I've put together a few images that are of different formats, as you can see, and these are the ones we're going to explore today. And the one with .jpeg is the one that I want to start off with, and this is an image I took literally last week when I was in London. So let's go ahead and drag this onto our notepad and see if we can see anything. Obviously, you need a software that knows how to interpret these images. Notepad is not designed to do that. Notepad is just a text editor, and I'm trying to load 2 megabytes of content into this notepad, so I won't be surprised if it's crashed, but it's not. You can see some stuff over there. It says 2023 November 20. It has some time. It's taken with iPhone 13 Pro, so you can see how certain components are readable, but obviously this is not how you would like to read your metadata. I also have, let me minimize this because I want to open TIFF file. While I'm here, let's just drag a TIFF file and see what we'll see. So let's just go ahead and drag this mito.tiff because I just want to get this thing out of our way so we don't have to go through this exercise for every one of these images. Now, TIFF file is a bit more readable when you drag it to your notepad. You can see it says dimension order X, Y, C, Z, T. It tells you that there are X, Y coordinates, and then you have channels and Z if in terms of depth, and the time series if it is time. So it's not just a 2D image anymore. It's a multi-dimensional image. And it's an 8-bit image, and you can read some of this metadata, but if I keep scrolling down, the real pixel information will start somewhere down here, which obviously is unreadable right now. You need, again, a software that can read these images, which is ImageJ is one of these, and I have ImageJ open right here. Again, this, in case you don't know what this is, you're missing out on a lot, because I assume you're working with images, and for images, if you ever want to do any type of processing, ImageJ is this free open source downloadable tool. Just search for ImageJ, you'll find it, or Fiji, F-I-J-I, ImageJ. You'll find this. Anyway, let's just drag our JPEG image into ImageJ, and now you can see how nice the image is. And if you want to extract metadata, if you want to know more about this image, just go to image and show info. So here it gives you a lot of information. What is the title of the image? What is the pixel width, the height and size and pixel, and a whole bunch of information right there. So this is what metadata is, but this is not the entire metadata. In fact, if I go ahead and bring this TIFF image that we tried to open earlier, and if I go to image and show info, again, it gives you a lot of information right here. What is the pixel depth and what is the X, Y, and so on. It gives you a lot of information right here. It actually has, I actually extracted one image out of 165 images, and it remembers that when I actually saved that, and you see how it says the total size right there is 165. So there you go. All the information is down here. You see how much metadata there is. A lot. Okay, so I'll keep this ImageJ open, but let's actually go down to our JPEG image and start looking at this in Python. Again, if you don't know how to code, this probably is a good reason to start coding. So, and this is not that difficult. I'm using a library called Pillow here, and let's go ahead and run that line, and let's go ahead and open this image, and the image I'm going to open is the Tower Bridge image. And if you look here, if I go to Variable Explorer, you see this image is 4K by 3K. You kind of get your information here right away, but this is not what I mean by extracting metadata. We need to extract our EXIF data that's embedded within the JPEG file. And the way you do that is once you have your image object, you just do get EXIF, and now you have the entire EXIF data right there as an object. And now you can actually print for each tag, give me the value in this EXIF, and right there. So you see the information right here, okay? And including iPhone 13 Pro. Now, what does it mean? Like you have 271 here, 272 here, 305. These are all the tags, and JPEG actually defined a whole bunch of tags, okay? For each this number, it basically means in this case, who's the manufacturer. This is probably what is the specific device it's actually taking on, what is the operating system, for example, what time it was actually taken, and probably other coordinate information is right here. So each number means, and go ahead and look at the JPEG documentation. I have this tags for our next exercise, but that's what these tags actually mean. Okay, another print command here, so we can just look at these. Yeah, I captured EXIF as a dictionary in this case, and you can print the dictionary if you want. But let's open the dictionary. The reason I'm using this Spider IDE is it's a great teaching tool. I just captured the entire EXIF information into a dictionary, and now I can open the dictionary. Now you can see individual attributes here. You can see the aperture value, the brightness value, date, time, and a whole bunch of information down here. Software, you can see 1703, and location, there is a location right there. So all the information is stored. Okay, enough about JPEG images. I know you tuned to this for scientific images, so let's start with DICOM images, because this is the easiest one when it comes to metadata. DICOM is digital imaging and communications in medicine. So obviously these are medical images. Well, not all medical images, but these apply to most medical images. And these are all radiography images. And it's an international standard for medical images primarily. And they were originally defined by the American College of Radiology and National Electrical Manufacturers Association, NEMA, in 1983, where they formed a joint committee to actually address this aspect of having digital images but no metadata to track along. And today these DICOM standards are managed by Medical Imaging and Technology Alliance, which is part of this NEMA. organization. And metadata in DICOM actually includes information about, as you can imagine, image data, size, dimensions, blah, 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 and includes patient information because these images are medical images. They come from some patient. That's also embedded into this DICOM images. Now, how to open these images in Python? I am using PyDICOM. There are multiple libraries, but PyDICOM is an easy to install. It's just pip install PyDICOM, and there you go. Now you can open DICOM files. I downloaded a test DICOM file. I don't have a source to create these, so I downloaded them from this link, and you can just do a quick Google search to download these. Okay, so with that information, let's go ahead and read our PyDICOM, import these methods, import these libraries, and now I'm reading the PyDICOM data, the brain.dcm, and let's go ahead and read this data set, and now I captured this image as a variable. Now let's go ahead and access and print the metadata, and the metadata is again embedded as part of the DICOM file. And if I just print the DICOM metadata and print the patient name, for example, and the patient name is, since we captured this DICOM data right here, DICOM data, within DICOM data object, we can actually call various, like for example, patient name, patient ID, modality, image type. So let's go ahead and print these so you have a quick idea of what to expect here. So patient ID is 7. Obviously, it's not going to say patient ID is John Smith with so-and-so social security number. You need to hide that information. So patient ID is 7 right here. And modality MR, which I think is magnetic resonance, MRI image. And image type is original, primary, other, or IR. So that's the image type. And we'll have a quick look at this image in a second, actually. Yeah, let's plot and have a quick look at this image so you know exactly what we're dealing with. Now, you can access metadata using the tags. Remember earlier we saw like 257 and some numbers with some values. In fact, let's go ahead and look at this. And this is the DICOM library. And look at the tags here. Let's accept the cookies. For example, 008, 032. That basically means acquisition time. So someone actually defined all these standards and specific tags, so you can look it up based on tag and print them out. So that's exactly what I am trying to do down here. So access the image type using a tag of 0008 and 0008, which is what? 0008 and 8, which is the image type. Right? So if we want to print that out, let's go ahead and look at DICOM data and give the tags. Of course, if you want to type these integers, you cannot just in Python put 0008. That's why I put like this 0x0008. I don't want to get into details, just Google search. You'll find the answer. So for that tag, go ahead and report the value. That's what I'm trying to do here. So let's go ahead and do that and print it out. And you see how we get original, primary, other, or IR, and so on, right? So this is nothing but DICOM data.image type. So instead of just doing image type, I'm just looking it up based on the tag, whatever is convenient to you. So yeah, physician name, there is another tag right there. So let's go ahead and see if they have any physician name here. No, they did not include. Just because you have metadata defined doesn't mean someone filled that field. So you may not see anything here. So in this case, no one filled what the physician's name is, so that is empty. So you may have standards, but people don't follow standards. This is demo data. Obviously, that's why they didn't have this, but you will see real useful metadata missing in some real useful data sets, which is a shame. Don't do that. And okay, so let's go ahead and for this DICOM data, I'm just getting the pixel array, which is nothing but the actual image information, and I'm plotting it out. And let's see how the image looks like. And there you go. And this is how the image looks like. It's too faint, right? Now, there are many ways to enhance it. I just wrote a few lines of code. Again, no point in going through it. I'm going to share the code with you so you can look it up. I'm just doing some equalization right there to enhance this image. And obviously, you see the difference between that image and this one. Now you can see all the details in here. So this is the image we are referring to, and the metadata is easily available. Again, you can use many different types of software to extract metadata for different types of images. For MRI images, there is a lot of other software out there. You can also use ImageJ, but ImageJ may not display the entire. Okay, let's actually open ImageJ and see what ImageJ displays for this file. DICOM. Oh, that's not bad. I didn't need to process the image. It's auto adjusting it, and let's go and look at show info, and this is all the information that's included here. Oh, that's not bad. ImageJ is doing an amazing job in displaying the entire metadata that's actually available as part of this image. So if you go to 00800, this is image type is original. You see, this is what we just ended up printing earlier, and referring physician's name is empty. There is no physician's name right there. So if you don't want to code, if you just want to look at this metadata, save it, just open it in ImageJ and you have all the metadata. Okay, moving on from DICOM images to TIFF images, which is probably the most common image format when it comes to scientific images. TIFF is, again, it was originally introduced by Aljus Corporation, and the first version of TIFF was released in 1986. But Adobe actually saw a very good opportunity in here. In fact, I think the original requirement, the need, arose from the scanners. You know, you used to scan all the images and you store them, and TIFF became a natural format to store these images, and Adobe jumped on this opportunity, and they became involved in this development and standardization of these TIFF. And today Adobe holds the copyright on this TIFF specification, which means they are the ones who are actually maintaining the metadata and guiding us into what the right metadata is. It uses a structured format called image file directory. So this is embedded into the TIFF file. This metadata is in image file directory format, and it contains tags, again, that defines various metadata fields, again, image dimensions, color space, compression, and you can actually take this TIFF and extend it to specific applications, which is what we'll talk about in a minute. And of course, like any other metadata, you have a tag, you have a unique identifier like a tag ID, just like we saw with DICOM and JPEG, and it's associated with a specific metadata field. Again, you can get more resources by following this link, but let's first, we already did this exercise of pulling the TIFF image into our notepad to read some headers. Now let's go ahead and use a library called TIFF file, obviously designed to handle TIFF files, and open our mito.tiff, the image that I just showed you, and go ahead and print the tag name and the tag value. So let's go ahead and do that, and this can be a bit messy. Now we have a lot of stuff here, as you can see, and this is the metadata that we saw in ImageJ earlier in a very structured way, but you can see every bit of information right here. What is the minimum pixel value? What is the maximum pixel value? And every little detail. I encourage you to go read this, look at this, because if you are trying to recreate this image, if you have a similar sample, then you may find this information useful, and what information you'll find useful, it completely depends upon the situation. If you're trying to use the same microscope, right? If the microscope vendor did a good job, they would have actually included all the relevant information under which that original image was collected, in which case you can extract that and you can set your microscope exactly the same way and recreate the same experimental conditions for your new sample that you're working with. Okay, now let's extract some metadata and print the TIFF image here. Let's just load another image that has been modified in ImageJ. So I changed the pixel size in ImageJ to 0.2 microns for this same image, and that's what I'm reading right now. So if you want to see what all attributes are there, you can go ahead and print the attributes right here. So these are all the attributes that are actually present. When I say attributes, how do I know what information to extract? Well, you can extract information like, okay, is this how many samples per pixel, how many segments, and what is the shape, and what is the subfile type, and is this image a GeoTIFF image? It will say yes or no. Is this image ImageJ? Meaning, has this been modified in ImageJ? I think that's what I'm trying to print here. TIFF image dot is ImageJ, right? I looked up here and I say, okay, that's available. So let's go ahead and do that. And let's go ahead and print it out. Does this image have image metadata? True. So it says yes, it does have metadata. Now let's go ahead and print out image underscore metadata. I'm sure it's probably somewhere up here, but let's go ahead and print image underscore metadata right there, and there you go. This is all the metadata that's under the image metadata. And you can do pixel width and pixel height and all the basic stuff. Okay, now we talked about tag identifier, right? So again, I can click on this and you'll see very similar documentation here. If I go down, you see how there is a tag number in decimal or hexadecimal format and what it actually means. Yeah, is image length and compression, what is the bits per sample, and so on. So you can use these tags to print out certain metadata, and that's exactly what I'm doing down here. So I'm just using some of these tags to print out some relevant information. So let's go ahead and run this function and go ahead and load an image. This is again another image that I have, and let's print out the metadata. Oh, let's print the metadata actually. So for each key value pair, let's go ahead and print, and there you go. The width is this much, height and color space and bit depth and so on. Okay, so all the information is down here. So I hope TIFF makes sense. And how the metadata is stored, again, I have it in the notes. Go ahead and look it up. Now let's go to GeoTIFF, and I'm sure most of my audience, you are working with these GeoTIFF files, and it's an extension of TIFF file basically. And it's an extension because the original TIFF file doesn't have the geospatial metadata information. So that's again something that you add in this GeoTIFF. So you can store the geographic information along with the raster data. Raster data is your image, your 2D. It can be 2D multi-channel, by the way. And it's in the form of tags. Again, the metadata is stored in the form of tags within the TIFF file, just like regular TIFF file. And it's who maintains this again. So the GeoTIFF standard is maintained by Open Geospatial Consortium. So they are the ones who kind of define what this metadata needs to be. Okay, so to read this in Python, I'm using Gdal here, and it's pretty straightforward to install it. Here you go. Follow the instructions, but let's go ahead and import our raster IO library, and I have a GeoTIFF right here that again I downloaded from a quick Google search. So don't ask me to distribute these images. I don't own them, other than the London Bridge image. I don't own any of the other ones. I just downloaded from Google search. Okay, so here you go. This is the image. You can see a GeoTIFF image. Now let's see, is this a single band, multi-band? It probably is a single band image. You can have multi-bands, right? So if the same image is taken using multiple bands, so you can have, but let's go ahead and count the number of bands and go ahead and print it out. So number of bands in this image is only 1. And let's go ahead and extract that one band. If you have multiple bands, then 1, 2, 3, get individual bands out, and then go ahead and print the tags for that specific band, and there is apparently nothing here, so there's nothing to see over there. Now to find out the coordinate reference system, again there's something specific and unique with GeoTIFF files that doesn't apply to regular TIFF files, and some of these are like coordinate reference system is one of those. And coordinate reference system is EPSG 32617 in this case, and metadata equals to, now we assigned this to an image, right? So raster.io.open, when we opened this image, we assigned it to a variable called image. That's what I'm using here. So go ahead and give me image.metadata and print it out. Python makes everything so easy. So there you go. Metadata, width, height, and transform, what type of transform, affine transform in this case, and so on. Descriptions, if there is any descriptions, let's go ahead and print it out. So there's absolutely no description with that. And to find out what geotransform, we already know it's affine right there from the full metadata, but you can print it out and look at the matrix right here. Okay, so that's everything about GeoTIFFs. Again, there's not much for me to add other than you going and exploring this by looking at what various tags are present and can you extract certain information. Again, just because there are tags doesn't mean the person or entity, whoever collected this image, filled that specific information. It's just that that information is you can provide that information if you want into the metadata, but that doesn't mean that information is there. Okay, now moving on to microscopy images. So OME TIFF, I'm not sure if I should say this as a standard, because microscopy never, I mean, I don't think there is a standard like DICOM for microscopy, but OME TIFF is as close as it gets, which stands for Open Microscopy Environment Tag Imaged File Format. So obviously this is an extension of TIFF, as you can see, and it's a file format designed for microscopy images and of course also for respective metadata. And it's an extension of the TIFF file, although there is a next generation standard that is being defined, because these files can handle only up to certain amount of number of dimensions. Now the microscopy world is getting more complicated with multi-dimensions, large data and all that, so the traditional metadata, traditional format is not enough, and the community is working on in defining the next generation formats. But let's stick with OME TIFF for now. It aims to provide a standardized way to store multi-dimensional microscopy data. Again, multi-dimensional is key, and it stores metadata in a structured way. Unlike TIFF, well, in addition to what TIFF actually does, OME TIFF stores metadata using XML, and this XML is embedded within a TIFF file. Yeah, this XML file is embedded within the TIFF file, and it contains all the information about microscope settings, acquisition parameters, and any other relevant metadata. And it sticks to OME data model. There is a data model that has been defined. In fact, if I go to OME model link right here, I'm including all the useful links right here. You can see the OME model is a specification of storing data in biological imaging. This is another issue when it comes to microscopy, because microscopy is used by biologists, by geologists, material scientists, you name it, like almost everyone. These standards are defined, as you can see clearly mentioned here, for biological imaging, and they can be extended to other fields, but that's why there is no microscopy standard. There are certain standards that apply to certain domains within microscopy. In this example, biological imaging. Okay, so I'll let you go through this documentation on your own time, but when it comes to Python, OME TIFF files can be read using TIFF file. Of course, this is, after all, a TIFF structure, and but OME TIFF can handle multi dimensions. For example, a time series, Z-stack, and multi-channel. This is beyond traditional TIFF. So you need some specialized libraries. So we are going to explore something, a library called Appear OME TIFF library that can help us read the image, but more importantly, extract the XML from that image. So we can just do whatever we want with that metadata. So first, let's use the TIFF file and print the attributes. So this is, again, all the attributes. Very similar to the exercise we have done before with regular TIFF. Here we are talking about OME TIFF, and it looks almost identical, right? So these are all the attributes. Now let's go ahead and use our Appear OME TIFF library. And when you read your OME TIFF using this library, you get two entities. One, your actual image, which is the NumPy array, and the other is the XML file. And that's exactly what we're going to print. So I'm not sure why am I printing the image instead of plotting it, but that's okay. So the image shape here is 1 by 3 by 1 by 1104 by 1376. That means I believe this stands for example, number of channels. This stands for which image is this? Yeah, this stands for number of channels. This stands for the number of time points. This stands for the Z. So we only have one plane, one time point, but with 3 channels of size this. You see how you pretty quickly got to a state where you have multiple dimensions. Okay, now let's print the OME XML that we extracted from this specific file. So if you can scroll this is everything you need. Now, once you have the XML file, you can extract whatever information that's stored here. It's pretty extensive, as you can see. So dichroic reference, I mean, right there, and what emission filter was used. So it has a lot of acquisition information and other information right there. Instrument, right? See, objective, what medium it was imaged in, its air, and yeah, lots of information, right? So this is great. And I mean, we talked about this image. We may as well have a quick look at this image. Again, this is 3 channels, so I'm printing 3 channels in separate grids up here. So you can see channel number 1, channel number 2, channel number 3. Obviously, a biological a tissue image showing you a whole bunch of nuclei here and a whole bunch of cytoplasm. And these, I believe, it could be mitochondria, but it's different markers highlighting different organelles within your cells. Okay, I am going to use exactly the same image, but now I'm going to look at the original image, which is .czi file. What is .czi file? Microscope manufacturers, in this case Zeiss, they often develop proprietary formats like CZI or Olympus has their own, Nikon has their own. There are many reasons why they want to come up with their own file formats, because I think I elaborated them here. So first, efficient data storage. Proprietary formats, they are probably optimized for efficient data storage, and which can be crucial because during high throughput imaging, you don't want to waste time writing it to the disk. They need to find an efficient way of actually handling those, and specific file formats may actually help in achieving that task. And instrument control and integration, obviously these software are designed to control the instrumentation, so proprietary formats often they're tightly integrated with this, and this integration actually enables the seamless communication between microscope and the hardware and the software. So because you want to accurately capture what is being scanned, and again, proprietary file formats can actually help them, these microscope vendors, in keeping track of that. Advanced features and compression. Again, some proprietary formats may support advanced features. For example, you have multidimensional data, time series imaging, and specialized compression algorithms are actually used to reduce the file sizes. So they can be optimized if they have better control over these file formats. And finally, they're all businesses trying to obviously generate revenue, so they can invest that revenue back into R&D, so they can give you much better products in the next generation and so on. Obviously, you understand what business is. So market differentiation is very important. So manufacturers may use these proprietary formats as a means of product differentiation. So having a unique format can encourage, I mean, you can have ecosystem built around it, around these image file formats. Okay, so enough about that. Let's have a look at .czi file, which is the file that I have in my hand, but it's safely extended to any other proprietary format. Not everyone makes this available, like extraction of this metadata or loading these proprietary formats available, because most of these companies, the software allows you to save the data into, for example, OME TIFF or any other format. So if you're not happy with this, you can always save the files in any other format, but proprietary, images, they have a lot more metadata potentially associated. Let's have a look at it. And in this case, Zeiss is nice enough to allow a library that, to publish a library, Python library, that gives us power to extract all the information, work with these files in Python. Go ahead and pip install this, and let's go ahead and load this image, exactly the same image as you see on the screen up here, but in its native format as .czi. Now, the best way to read this is in the context manager, this image. So I'm going to read this image and print out the raw metadata to see what we have. And this, let's clear everything. Let's actually clear the screen here and print this out so we know exactly what's going on. There you go. This is the XML file that has all the metadata. We just cleared the screen so you see how much metadata is available. In fact, I'm not even seeing the top portion of it, so I'm just seeing the bottom portion of it. Every little detail is included here. So you can take, like, I can see that, okay, Alexa Fluor 489 is one of the dyes that actually used for epifluorescence. So I can read every little detail here. So this is, now I can prepare my sample by looking at this. I can set my experimental conditions by looking at this metadata, and I can actually hopefully reproduce the same image based on this metadata. That's one of the advantages. That's one of the reasons why it's important for science, to keep track of metadata, for scientists to keep track of metadata. Okay, so instead of sifting through this entire thing, let's go ahead and print a few things. What do we need to know? Oh, by the way, if I go to Variable Explorer, we save this as part of, in fact, MDXML. Where is this? MDXML. So here, this is MDXML. Let's actually save this as a dictionary, so we can actually go ahead and explore it. So first thing first, actually, let's just run these lines so you can see how the dictionary looks like. MD dict right there, and you see how we have an image document right there, and within image document you have metadata. Within metadata you have display settings, experiment, blah blah blah. And if you want to look at the image scaling, let's open that, and you have image pixel size information, scaling component. You get, this is so deep. Display setting, how many channels do you have? Go ahead and open this. You have 3 channels. Open it. You have dictionary. So this is obviously we are just using the UI to extract all this information, but let's actually close this and print within image document, metadata, display setting, channels. So let's just print some information down here so you can clearly see. Okay, die name for channel 0, Alexa floor 568. That is for channel 0. You can print channel 1, channel 2, channel 3. You can see how we are doing it right there. Let's print more metadata just for the fun of it, because we have this. And you get an idea. I added a whole bunch of stuff because I know I'm going to share this file with you. But here, image dimensions, you can see the number of time points is only 1. Number of Z is only 1. Number of channels, we have 3 channels in this image. Number of H dimensions, I think this is number of scenes if I'm not wrong. But again, let's ignore that. X, we have a dimension of 1376, Y 1104. Okay, and the pixel type for all channels is gray 16-bit. That's the pixel type. Okay, now let's have a look at the image corresponding to the above metadata. So all we need to do is just run this, and we should see exactly the same image as before. There you go. This was the OME TIFF image. This is the CZI image. I'm switching back and forth between these two. There is no difference between them. There shouldn't be, because we're not changing data. Hopefully, when we save image from one format to the other, we are just changing the file formats. And metadata, again, it depends on what this other file format can accept as metadata. Okay, this is turned out to be a longer video than I anticipated, almost probably more than half an hour. But I hope it gives you a nice idea about metadata in general and what it is, how it is stored. By the way, in CZI, it is actually stored also as an XML file. So in most cases like JPEG and TIFF, you have the metadata embedded within these files in XF format, for example, in JPEG. But when it comes to GeoTIFF, also uses the TIFF native tags, but OME TIFF has an XML. CZI file has an XML because there is so much metadata that needs to be written. And when you export these files, when you export a CZI file into TIFF, it always exports it into a TIFF file and an XML file. So you have all the metadata written in XML, because TIFF cannot accept all kinds of metadata that is actually relevant to microscopy. Okay, so I really hope you learned something in this video tutorial. And if you have any questions about any topic that you want me to cover, and if I know what it is, I will definitely cover it. So please leave that as part of the comments. And again, please do not forget to hit the subscribe button. Thank you very much.